Hi everyone, welcome back. It's Dr. Heath here, and today we're going to talk through section 4.2, which is all about prime and composite numbers. So by the end of this section, you will be able to describe what is a prime number and what is a composite number, figure out the number of divisors that any whole number has, as well as understand the fundamental theorem of arithmetic, which deals with prime factorization. So I want you to start out considering the number 18. With the number 18, we can visualize it in an array model by thinking of it as 1 times 18, where we have one row and 18 columns. We can also visualize 18 and its factors by thinking about how we could split up 18 and create these other visualizations that are rectangles. So if I take 18 and I split it in half, I can then stack the 9s on top of each other and get 2 times 9. Or I could split 18 into 3 groups of 6 and stack those 6s on top of each other and see that 18 can also be 3 times 6. So what we can see through this visualization is all the different factors of 18. These are actually the only ways we could split 18 up. We could change the orientation of the rectangles so that it was 9 times 2, kind of like a long, tall rectangle, or 6 times 3. But these are all of the factors of 18, factors or divisors. So the number 18 has 6 positive divisors, and they are 1, 2, 3, 6, 9, and 18. We can also think about classifying the whole numbers by the number of positive divisors they have. So this chart here shows us the numbers that are less than or equal to 37 in a column that designates how many positive divisors they have. In this chart, we can see that these numbers have exactly 2 positive divisors, and those positive divisors are 1 and itself. So, for example, if we look at 11, the only numbers that divide 11 are 1 and 11. So 11 has exactly 2 divisors. The numbers to the right of that column have at least one other factor other than 1 in themselves. So they could have 3 positive factors, 4 positive factors, 5 positive factors, etc. So for example, if we think about the number 10, the total factors of 10 are 1, 2, 5, and 10. So there are 4 total divisors, but they have at least one factor other than 1 in themselves if they're to the right of that 2 column. And something to notice is that the leftmost column is indicating the numbers that have exactly one positive factor, and that is just going to be 1. The number 1 is the only number that has only one positive factor, and it's neither prime nor composite. So we say that 1, it's not prime and it's not composite. So we finally formally define what is a prime number. A prime number is any positive integer with exactly 2 distinct positive divisors. We can also define a composite number, and that's any integer greater than 1, so 1 does not count as composite, any integer greater than 1 that has a positive factor other than 1 in itself, so more than 2 factors. All right, so we can show that numbers are composite, and the way we show numbers are composite is by showing that they have at least one factor other than 1 in itself. So when I look at 1,564, I immediately recognize that 1,564 should be divisible by 2 because it ends in an even number. So since 2 divides 4, the last digit of the number, 1,564 is divisible by 2, and therefore it's composite because it has a factor or divisor other than 1 in itself. When I look at 2,781, I go back and I try to remember my divisibility rules. I know that it's not going to be divisible by 2 because the last digit, 1, is not even. But I could check for the divisibility rule for 3, which is I add the digits together. So I say 2 plus 7 plus 8 plus 1. And that should give me, I've got 10 plus 8, 18. And so I know 18, 3 divides 18. So 3 will divide 2,781. So since 3 divides the sum of those digits, I know 2,781 is divisible by 3 and is composite. All right, if I think about 1,001, I can again start to think through my divisibility rules. I know that it's not divisible by 2. I can tell it's not divisible by 3 because 1,001's digits would sum to just be 2, which is not divisible by 3. If it's not divisible by 2, then it can't be divisible by 4. It's not divisible by 5 because it doesn't end in a 0 or 5. It's not divisible by 6 because it's not divisible by 2. I could try 7, but actually I'm going to see that 1001 is divisible by 11. And remembering that the divisibility rule for 11 is if the sum of the digits in the places that are even powers of 10 minus the sum of the digits in places that are odd powers of 10 is divisible by 11. So I take the digits in the even powers of 10, so that's going to be 0 and 1. Those are my even powers of 10, so I sum those digits, 1 plus 0, minus the sum of the digits in the odd powers of 10. So the odd powers of 10 are here, remember, because this is 10 to the 1, this is 10 to the third power, this was our 10 squared power, and our 10 to the fourth power. So I subtract, again, 0 plus 1, my odd powers of 10 places, and I see that that's just 1 minus 1, or 0. 0 is divisible by 11 because 0 times 11 equals 0. So, since 11 divides 1 plus 0 minus 0 plus 1, 1001 is divisible by 11. So I found a factor of 1001 other than 1 in itself, so it is composite. Last but not least, I have 3 times 5 times 7 times 11 times 13 plus 1. This number I could multiply out and figure out what the number is without this expression of the product of these odd numbers plus 1, or I could remember that the product of odd numbers is always going to be odd. So I know that this number here is going to be odd. And so when I add 1 to an odd number, I get an even number. So since the product of odd numbers is odd, 3 times 5 times 7 times 11 times 13 is odd. When we add 1 to an odd number, the sum is even. And all numbers are divisible by 2. And all numbers, even numbers greater than 2, have to be composite. So this is a composite number.